Welcome back. In this lesson, we'll start a discussion on the near future of SDN, and in particular, we'll talk about what SDN has to say about network, compute, and storage more broadly, which is coming to be known as a concept called Network Functions Virtualization, or NFV. One of the issues that network operators face is that middle boxes are pervasive. And an interesting question to study is what SDN has to say about middle boxes. We've spent a lot of attention focusing on how SDN can affect the data plane as far as forwarding is concerned. But networks have firewalls, intrusion detection systems, VPN gateways, WAN optimizers, and a whole bunch of middle boxes that could conceivably be controlled from a logically centralized point. SDN, of course, promises centralized management of the forwarding parts of the data plane, but a reasonable question is whether it can also be a unifying framework for a more general set of functions. Network Functions Virtualization combines forwarding devices and middle boxes into a common control framework. Its promise is to enable network operators to implement network policy without having to worry about the nitty-gritty details of how it's actually implemented. Two implementation details we'd like to abstract are placement, in other words, where to place these functions inside the network, and steering, which is, once we've placed these middle box functions, how we should route or direct traffic flows through the network so that they pass through the appropriate set of elements or functions before they eventually reach their destination. The problems of placement and steering are incredibly hard. We need to figure out a way to map traffic flows and demands to both the available network resources, or the paths, and the available processing capacity of middle boxes. It's like an extremely hard traffic engineering problem because not only do you have to consider the available resources of the network, but you also have to consider the available processing capacity of boxes that are sitting in the network, and which, by the way, might be virtual. So you have the option not only of moving the traffic to existing middle boxes, but also the option of moving middle boxes to where the traffic is. So solving these problems just by themselves are extremely challenging, but we also need a unified abstraction for expressing the nature of the type of solution that we're looking for. In other words, we need a unified abstraction for control over network forwarding, data, and storage. One could call this problem more generally middle box orchestration, and a system that we've been working on called SLIC seeks to solve some of these problems. One could broadly classify this into the set of problems that NFV, or Network Functions Virtualization, is really trying to solve. The idea is that you want to augment your SDN controller so that not only is it installing flow table entries or things that affect forwarding behavior, but also middle box style elements or code that could perform more complex operations on the traffic as it passes through the network. So the controller is ultimately responsible for installing and configuring this code, or what we might call elements, steering the traffic through these elements, and also handling any callbacks that the elements themselves might generate. We want these elements, or the code that's representing middle box functions that could run in the network, to be able to implement arbitrary code. For that, we expose a common API through which a controller can install code and also interact and configure existing elements. A controller might then be able to use manifests that physical network devices use to describe the available resources to figure out the appropriate places to place these elements or functions at the appropriate physical locations inside the network. A SLIC application runs at the controller and implements some kind of network policy. That network policy determines which element or sets of elements should run on which portions of flow space and how to react to various changes in network conditions. It does not specify where the element should be placed or how the traffic should be steered or routed through those elements. Those details are handled by the runtime. The controller manages and configures the network of middle boxes. It implements resource discovery, much like a standard OpenFlow controller would implement topology discovery, except now we're discovering other types of resources as well. In addition to installing or removing flow table entries, this controller also deploys or removes elements that run on machines through the network. It also ensures availability of these elements in the face of failures. The controller ultimately implements whatever policy that the application specifies by automating element placement and steering traffic through the elements once they've been placed in the network. To do so, it uses online algorithms to ensure that resources are allocated efficiently and that traffic flows see good performance as they're processed by elements in the network. Let's take a look at a quick example of an application of this type of dynamic placement of middle boxes or elements. A network operator might, for example, want to inspect all DNS traffic with a DPI device, and then if a suspicious lookup takes place, redirect that traffic to some kind of traffic scrubber. This type of application involves a number of moving parts. One involves placement. Where should we place the DPI device? Another is steering. Once we've placed the DPI device or devices, we need to redirect DNS flows through those DPI devices that we've placed. Finally, we have an element of triggering, whereby if a particular event, such as a suspicious lookup, is detected by a middle box, we want that middle box to then send a callback or a trigger to the network controller that then updates flow tables to redirect network traffic to the appropriate locations. Whatever solution we come up with, we want to minimize the implementation footprint and also enable optimization for bandwidth, latency, and network resources. Let's take a look at the problem of placement in a bit more detail. At a high level, we're given a specification of different parts of flow space that should map to different sequences of elements. In other words, we might say that all port 80 traffic should be subject to a DPI element followed by a load balancer element. And we might have a collection of these specifications. Now our task is to place the sequence of elements or element graph inside the network such that resource utilization is minimized. We might consider minimizing the number of locations where we place these elements, minimizing the bandwidth utilization of placing these elements, or minimizing the latency of the traffic flows while implementing a particular policy. Let's say that we have an element graph, such as the one shown at the top of this figure, E1, E2, and E3, and we'd like a particular set of traffic flows to be passed through this element sequence. We could place those elements all on one physical middle box, but even if we did that, we have the decision of where to put it in the network. We could put it closer to the ingress, or closer to the egress, or somewhere in the middle. Placing the elements in the wrong place can actually have some pretty dire consequences for the traffic as it's flowing through the network. For example, if we put them in the wrong place, we might have cases where traffic flows boomerang through different parts of the network, causing higher bandwidth utilization, more latency, or more utilization of precious switch resources. So we need to figure out how to place this element graph through the network in ways that avoid these types of problems. Once we've placed the elements, we also need to figure out how to steer traffic through the network so that the flows actually pass through the right sequence of elements. Different source-destination pairs might be steered through different instances of the same element sequence or element graph. Finding the shortest path is not the only requirement for steering. It also needs to have properties aside from shortest path steering. For example, we might want to make sure that all traffic flows pass through a set of elements in a consistent order. We might want to chain elements or sets of elements in a particular order. We might want to enforce steering of traffic flows through a particular sequence of elements even when routing is asymmetric. Or we might want the element graph itself to be asymmetric. We also might want some of the steering to be dynamic. In other words, whether a flow passes through a subsequent sequence of elements in the element graph might actually depend on the outcome of processing from an element that's upstream in the graph. Let's take a brief look at dynamic chaining in a little bit more detail. We might want to enable path changes for packet flows based on certain conditions. For example, you might have a stateful firewall that inspects traffic flows that inspects the destination IP address of traffic flows and passes the traffic through either a DPI box or an antivirus proxy depending on the destination IP address. In this case, the chaining of elements actually depends on the outcome of the first element. We are still in the process of designing runtimes that efficiently place and steer middle boxes for these types of problems. One simple approach is to do an iterative placement and steering, where the network continually monitors link and machine loads, and in the case of overloaded elements, creates new instances of those elements. Subsequently, the controller can then steer traffic through those new elements. In summary, we're still in search of a programming model that unifies network, compute, and storage in the context of middle box placement and network traffic processing. In addition to the programming model, we also need a runtime that can efficiently place these elements in the network and steer traffic to the appropriate instances of the elements once they've been placed. Solving these problems needs both efficient algorithms for placement and steering, as well as the proper programming abstractions so that a network operator can simply define policies at a logically centralized controller without having to worry about the details of placement and steering.